Okay, microphone is working. People are dropping in. It's great that we have people showing up at 10 in the morning after opening party with an open bar. It's not easy, but yeah, so thanks everyone for being strong and waking up for this talk by me and Daniel. And yeah, Phantom to Inception. And Phantom is a primitive or a behavior we call Phantom, and we used it to create an exploit that's called Inception. And yeah, it gives you this interesting feature or bug where you can train the branch predictor without actual branches. So we'll start with like introducing not ourselves, but this person who is kind of the reason why we know each other and started working with each other. So this is our Mr. Professor Dr. Kave, and he wanted to break red pooling a few years ago. And then he hired me as a PhD student, and I made red bleed for him, or for us. And then while I was working on that, it turned out that that thing was going a little bit deeper than just reds. So as the name maybe already gives away, red bleed was about returns. Yeah, so he didn't really believe me what I was saying, but he found a student that had the time and enthusiasm to look carefully at this. We just had to feed him with a lot of caffeinated beverages, and then he started working, and eventually he found that actually this thing that looked like a programming bug actually was something that you could exploit to leak memory. And that's later got the name Inception. At least that's the name we gave it. It's not a very good name for SEO or for grepping stuff in the Linux kernel, so they decided to call it SRSO, or Speculative Returns Stack Overflow, or something like this. So that's that, and we're going to get into what all of those things are. But yeah, that's our reaction to Daniel. And yeah, we were at the ETH at that time, and now Daniel abandoned us and went somewhere else. He's now in the MIT. Okay, so this red pooling thing, if you have disassembled the Linux kernel, you maybe have an idea what this thing is, but with the Spectre attacks, this instruction was considered harmful or problematic. So red pooling's task is to get rid of this. So we just replace indirect branches. So this is what we call an indirect branch. We just jump to the whatever pointer is in the register value. We replace it with this cute-looking snippet of code. And if you think this looks a bit hairy, it's nothing to compare to what it looks right now today. So this has the property of predicting branch targets with a branch target buffer. So as you may suspect, this talk is about speculative execution, which means that we are not really able to make a decision about where to branch yet. We don't necessarily have the register value here, so we have a branch predictor that's just going to go and provide a branch target before the value of the register is known. For example, it could be because it depends on things that depends on memory, and it could be slow. And we never want to slow down or like stop having units on the processor like waiting for stuff. So we always, branch prediction is an essential part. Yeah, and we replace this one now with a return essentially, and the return has this property of being predicted by a different mechanism. So some kind of return target predictor. And it has a backing store that we're going to refer to as return stack buffer. People have also referred to it as a return address stack or a return address predictor. So we have RAS, RAP, and RSB for essentially the same thing. And this return has been like made so that, yeah, so you see before the return, we move actually the branch target to the stack pointer, and then the return is going to consequentially now return there. But before, so we actually override our return target, the original return target is pointing to the pause instruction, which is where what the branch predictor is going to pick, and then we're going to mispredict every single ret boolean branch or indirect branch to execute this pause elfence infinite loop. So now all indirect branches are safe, but they are also mispredicting. Well, that's what people thought at least, except there were some problems with returns because they are very similar to indirect branches. So as you can imagine, things can go wrong for returns as well. There are special conditions. For example, this return stack buffer has limited size. For example, it can be 32 or 31 or 16 entries. And of course, if you have a really deep call stack, at some point you're going to consume all of those entries. And it would be good to be able to predict that return without then, even though you don't have a valid entry in your return stack buffer. And then you can use branch target prediction. So anyway, this is what it looks like now. We don't even have a return here. We have like a jump to somewhere else, which is going to do a return, and we will get to why it looks like that. Now it has something to do with what we're going to talk about. But yeah, so we're going to talk first a bit about phantom speculation. So, and yeah, we start with this question. So now everyone has to like think in the morning, like get a question at 10 a.m. It's like annoying, of course, but yeah, so I'm asking like, what is common to all Spectre attacks? It's also a very vague question because they have so much in common, so hard to answer. But I can, to show you a little bit what I'm trying to get to, here's like an example of a potential speculation primitive for variant 1, where you have a conditional branch. So we have a comparison, and then we have a conditional direct branch here. And what Spectre attackers found that they could do was they could turn this conditional branch to either be fall through or taken when the actual resolution of the branch would be the opposite. And of course, then you have like a speculative control for path that is invalid or incorrect. And yeah, ultimately you can use this to leak information. And here's the Spectre variant 2 example here. Where we just have an indirect branch, like I showed you before, except now it's in like some kind of Intel-like syntax. Before it was like more AT&T looking. And this one is extra nice because this gives an attacker ability to not just say the branch is of course always taken, but the target can be anywhere in the address space. So if you can control the branch target here, you have much more opportunities than with Spectre variant 1. So what is common with all of this is, of course, the presence of a branch. Even the little ghost here is holding a branch. So that's yeah, that seems obvious. But let's see what happens if we lose the branch and swap the eyes and see if we can do branchless Spectre. That would mean then that we have branch prediction on like arbitrary instructions, like can we make like some arithmetic instruction behave like a conditional branch? Can we make like some XOR thingy behave like a direct branch or indirect branch? That's basically the question. It maybe sounds a little bit out there to ask such a question, but it also makes sense if you think about how a processor works. We think about processors that they have these pipeline stages. So we fetch instructions from memory, and then we need to decode them into micro-ops, and then we can dispatch them for out-of-order execution. And eventually, if all the dependencies for an instructions are met, then we can retire the instruction, and then it's going to be visible for the programmer, or it's going to be visible in the architectural state. But until then, it's only in the micro-architectural state. But the stuff that is happening in the micro-architectural state is, of course, still using the load store unit of memory operations and all the execution units, so they still have side effects. And before we know where to fetch instructions, we need to have a target to fetch from. So that's what the branch prediction part is doing, so that we can think of being the first component of this pipeline. And so imagine we fetch some instructions. We need to decode them before we know whether it's a branch here. But the fetch unit has just fetched. So should it just sit around and wait until the decoder is ready and comes back and says that, oh yeah, we have a branch here, so now you should do some branch prediction on top of that? The answer is like, not necessarily, or no, it will not do that. And in fact, these different stages are like much more separated from each other. We think of them as like completely isolated modules. And they don't necessarily know much about each other at all. So they just have queues. They just communicate with some queue. You get some information from your input queue, and you process it, and then you produce some results for your output queue, and that's the input for the next stage. And so when we have a new branch prediction, we can put the fetch target in a fetch target queue, and then whenever the instruction fetch unit is ready, it can fetch this. We might believe that we are going to fetch in code that contains a branch in this block of instructions that we're fetching. We might anticipate it. So we fetch this fetch target, and we get blocks of raw bytes. And now these blocks of raw bytes will then be processed by the instruction decode unit. And where we anticipated to expect a branch, we actually might just run into something that is not a branch. And when this happens, now we need to somehow notify the front end or the branch predictor that what you were anticipating is not going to actually happen. And if you compare this to classic Spectre, you have the case where you actually have a branch as you anticipated, but during execute you realize that actually the resolution of the branch is not what you predicted. So you get a re-steer that occurs. However, it needs to be emitted from the CPU backend, whereas the case of phantom speculation is detected already at decode. So things can go wrong here, otherwise we wouldn't give this talk. So you can imagine, like, we have already fetched the branch source, or what we anticipate to be the branch source, so we can already go ahead and predict the target of that. So what can happen is that we're going to start forwarding mispredicted control flow down the pipeline. And this is all used to be just the expected behavior of processors. So a CPU designer would be like, oh yeah, works as expected. That we are fetching and raw bytes of instruction, and they eventually go into decode. And it could even so happen that these mispredicted instructions actually go into the execute stage. And that's which is similar to how a Spectre would cause. So we were thinking we would try to capture and see how far a misprediction advances in the pipeline. So the first thing that we can observe is if instructions are fetched, because you got to fetch them from memory, and so they enter the instruction cache and the other caches, and we have tools for side channels to measure whether something is inside the cache or not. So that's the first one. And when instructions are decoded, then we cache the micro-ops from the decode as well, and store them in a micro-op cache or a data stream by it's called a decode stream buffer. Intel calls it, but a micro-op cache. And we can also, using timing, detect whether something is present in the micro-op cache. For our case, we were just wondering whether it exists or happens or not, so we just rely on performance counters to see whether this occurs. And finally then, if instructions are actually, or micro-ops are actually dispatched for execute, then if there are memory operations, they will have, they can affect the data cache, and that gives also, of course, a measurable trace. So now we have these tools to measure, like, whether a misprediction happens, and we can also see how far it advances in the pipeline. Whereas before we would only maybe look at whether mispredicted branch targets actually just execute. So With this, then we ask the questions like, what happens for these different types of instructions? What kind of how can we make those mispredict, and how far would such a misprediction go in the pipeline? So we tried all kinds of like type confusions between the decoded instruction, and we tried to make each decoded instruction get a predicted prediction associated with it that does not necessarily associate with the type of the decoder instruction. So, you know, classic Spectre variant 2 is like we have an indirect branch, and then we train it with another indirect branch to give it a new branch target. But there are all these other cases. For example, we can have a indirect branch, we train it with direct branch prediction. So we looked into all of these, and we see that actually all the time we have the front end fetching the branch target that we train it with, and in particular we see that the behavior of the branch is not like the decoding instruction, but what the prediction, how we make it predict. So a return or like a direct branch would we could make, for example, a return and predict like a direct branch. And yeah, some of these cases here have been talked about in the past. So the case where we predict no branch, but we actually have a branch, has been referred to as Spectre SLS, straight line speculation. So it means that you're just falling through, even though we have, for example, a return, we start executing instructions behind it. So maybe you've also seen that in if you disassemble the kernel, that every single return has like a int 3 instruction behind it to just stuff the pipeline with junk so we don't get straight line speculations after returns. And then the case with retbleed is where we have a decoded return that is behaving like an indirect branch. And then the case where we have like branchless Spectre that I just hinted at in the beginning of the talk is, yeah, then we have not a branch, we decode something that is just like arbitrary instruction, but we make it behave like one of these branch types. Right. So now the question is whether we should be concerned about this at all. Like, after all, this speculation issue is like very short. So the mispredicted instructions rarely even reach the execute stage. So the question is, can these mispredictions, are they exploitable at all? Should we be scared about this kind of ghost behavior? And I will let Daniel talk a little bit about what we can do with phantom speculation. Like this.
All right, so we built a number of exploits using Phantom. So the first one is that our first exploitation primitive, P1, allows us to detect whether a virtual address is mapped and executable in a different security domain. Then we can do something similar for data. And we have a third exploit that allows us to leak sensitive data. And because the first two are a little bit similar, we'll be talking about the first and the third exploits. So how do we detect whether a virtual address is mapped and executable in a different security domain? So this relies on, we rely on the fact that an instruction fetch only succeeds if the target of the fetch is both mapped and executable. And so if we can somehow observe whether an instruction fetch succeeded while running a victim, we can figure out whether the target of the fetch is mapped and executable, and thus we can break defenses that rely on keeping this information secret, such as kernel ASLR. So the attack setup is something like this. We have an attacker that runs in user space, and the attacker wants to figure out where the kernel lives, at which address. And so the attacker goes over all the possibilities of where the kernel could live. And for a particular guess, X, it will first poison the branch predictor. And it does this by simply jumping to the guess, X. And of course, this is illegal behavior. So this will give a segmentation fault, but it will prime the branch predictor with a prediction that there exists a jump to X somewhere. And then the attacker just issues a system call. And if the attacker did step 1 correctly, then the prediction to jump to X will be consumed by the code that is executed in the kernel now. And so it will believe there's a jump, and it will try to fetch X. And if X is mapped and executable, meaning if X is the actual location of the kernel, then this will succeed. It will populate the instruction cache. And this is something that the attacker can measure using prime probe back in user space. All right, this is quite straightforward, but there's one step that is a little bit unclear. So in order to make sure that we consume this prediction to jump to X while we run the kernel, we need to make sure that we execute this jump to X at a location so that it aliases with the kernel address. And so this was actually already reverse engineered for Zen 1 and 2. But for Zen 3 and 4, this information was not known. So we had to do some reverse engineering. And we find that the CPU does a number of XOR operations on the virtual address to obtain basically a prediction in the BTB. So using this, it will index and compare a tag in the BTB. And because there's a lot of overlap, particularly bit 47 is used by all of these functions, it is infeasible to brute force this. So we had to use other techniques, including SMT solving, to figure out what these functions are. But with obtaining those collision functions, we were able to break kernel ASLR on all Zen CPUs, Zen 1 through Zen 4. And on Zen 4, it takes a little bit more than a second to break kernel ASLR. But of course, we want to do more than breaking kernel ASLR. We want to leak data, ideally. And so we consider the following example, where we have some victim application that loads a secret into a register. So for example, cryptographic code that loads the secret key and then does some operation on it. And so we considered what would happen if we trigger phantom speculation right after loading the secret into the register. And then we try to execute a memory load in this window that on an address that depends on this register value so that we can recover it using prime probe attack. So we evaluated this, and we find that this works on Zen 1 and Zen 2. So this is because on those machines, phantom speculation proceeds so far in the pipeline that we can do a memory load, whereas on Zen 3 and 4, the misprediction is corrected much quicker, and so we cannot trigger such a memory load. But we can even do a little bit more. If we combine Spectre with Phantom, we actually obtain a novel arbitrary memory leak. And so here's an example. We have a code snippet that checks some condition, and if this if statement is mispredicted, we end up having an out-of-bounds memory load. So we can arbitrarily load, or we can load an arbitrary address into a register under speculation. And so a typical Spectre v1 gadget would now have another memory load that loads that secret value, or sorry, that leaks that secret value using a memory load, a second one. But in this case, this gadget doesn't do that, and we call those gadgets MDS gadgets, microarchitectural data sampling gadgets, which are known to be exploitable on Intel, but were not known to be exploitable on AMD. And so with Phantom, we can now make these exploitable by triggering an additional memory load right after having the out-of-bounds load using Phantom. So we basically have nested speculation. We have a conditional branch misprediction, and in that window we have a Phantom misprediction. And according to previous work, this increases the number of Spectre gadgets by 4 times in the Linux kernel. So in conclusion, AMD and Intel CPUs do not only predict the target of a branch, but also the existence of them. And people were generally unconcerned with this behavior because it only gives you very short mispredictions. But we show that this still allows us to compromise system confidentiality. And furthermore, it is a stepping stone towards other attacks. And one of them we will talk about now.
Yes, OK. OK, it's time to try to run a demo. Let's see how this will go down. This is a machine. I should show you maybe something about it. It's like using pretty normal boot parameters, except for one little thing. For demo reasons, we reduced the available physical RAM so we can scan the address space, the available memory a bit faster. We can look at what kind of processor this is. It's like some, yeah, it's an AMD EPIC. This is actually Zen 2. We can also look at what vulnerabilities, and also maybe we should also look at what kernel this is. So this is 5.19, which was the latest we could find in the Ubuntu repositories when we carried out this work. And what should we look at here? It's mitigating red bleed. That's good. Gotta do that. And then Spectre variant 2. Those are the ones that are relevant for us here, I guess. Yeah, so we're using ret booleans for indirect branches. The rest here is for yeah, sibling threads and for cross-context problems. And for ret bleed, we are using untrained return func. So this is we're going to get into a little bit how we do untraining later. OK, so should I just try to run this and see what happens? Oh yeah, now there's the question whether we should use demo 1 or demo 2 here. It's always like that. I guess I'll just run this one, and then we see what happens. It has a whole bunch of Tmux panes here, so each one is like running its own independent instance, which is a bit suboptimal, I would say, but we were mostly just interested in being able to make it work and not optimize it. So what is happening here is like, yeah, we find the kernel text, yeah, where the kernel lives, and then he finds the physical address of some memory that is in the physical address of the memory in the attacker's address space, and then it finds the beginning of the linear memory map or FIS map, and we know that FIS map plus the physical address of our memory is going to give us a kernel virtual address that is accessible inside our attacker's address space because of supervisor mode access prevention. We are not, the kernel is not allowed to touch user memory because of, not because of Spectre, but because of attacks like ret to dir and stuff like this. So I think we will just let this thing run. Oh, you can see, actually, I was thinking to just let this thing run in the background, but we could see, actually, what is this? It says it's found a secret, but you know, sometimes it finds other stuff. This looks like, this does not look like the secret that we were looking for. We were looking actually for the, root password hash. It's leaking something else. So basically, it just looks for something that starts with root, and then if it finds that, then it tries to see if it can leak that information. This does not really look like something super security sensitive at all. But we can just let the other instances sit in the background, and then we can come back to it a little bit later. Or actually, I could also start another instance, I suppose, on another machine, actually. So here we also have another guy. So we can run this one too. There's also a Zen 2 same kernel version and such. OK, let's go back to the next part of the presentation. So we use phantom speculation to build a more interesting exploit. But now that you know how phantom speculation works and a little bit what you can do with it, we'll basically show you to what extent you can take this primitive. So we built Inception on, first we made it on AMD Zen and Zen 2. We wrote a paper and submitted it, but then meanwhile during the review process, Daniel found that actually we can do this on Zen 4 as well. So this little GIF demo here is doing it on Zen 4, which we were excited about, and then we had to change a lot in the paper because it became very a lot of new information. It became very dense. I don't know if you have seen the paper, but we welcome you to take a look at it if you want to get some more details about this stuff. A lot of people say that they read it many times. I don't know if they read it many times because they think it's so good or because it's difficult to understand it. anyway, this works. This one took 40 minutes. It goes a little bit faster on than 1 and 2. We have higher cover channel bandwidth there. So these ones are compromised, and these ones are compromised. Yeah, this is what we show when something is broken intuitively. Okay, so with Spectre attacks, we have some shared state between an attacker domain and a victim domain. Oh, where's this one? Okay, attacker domain and a victim domain. So in this case, for tradition, we always have an unprivileged attacker targeting the privileged kernel domain, and because they have this shared microarchitectural state between them, we can do some interesting Spectre attacks. So what the attacker's goal is to hijack a branch in the victim domain and make it misspeculated to execute some gadget that enables them to leak privileged memory, in this case, or memory from the victim domain. And the way they do that is by executing a branch in their own domain that maps to a certain branch predictor entry here. We just need to execute it from a particular address. Sometimes you need also to use a bit of path history or like branch history, but yeah, you need to the attacker executes a branch in their own address space from an address that aliases with this kernel address of the victim branch. Okay, and now we have a prediction here, and then they set up the cache in some way. For example, we flush a number of cache entries or cache lines before they trigger the victim to execute. Eventually, the victim reaches this branch instruction that is supposed to go elsewhere, but because of the training, it uses the branch predictor entry here to transiently, for a short time, execute this leak gadget. And now the leak gadget accesses memory, and we wanted to access some secrets and then use the secret in a dependent memory access. So we get a secret dependent trace in the cache that the attacker then later can infer using a timer. So this is how you would be able to do this stuff back in like 2017 or so. Yeah, this is too simple. So we need to nowadays you need to be you need to put a little bit more effort, but not that much. And this is because we have mitigations, which is a great thing in general. We have two types of mitigations. We have like predictor restriction and predictor sanitization, like these two classes. And this can be both enforced by software. So for example, if we know that this branch instruction here is vulnerable to Spectre attacks, we can just restrict the branch predictor from using such predictions by replacing it with a different instruction with similar semantics. So that's like a software method. And then we also have hardware-enforced defenses that restricts branch predictions that were learned in a different privilege domain from being used in the privilege domain of the victim. Exactly how IBRS is implemented depends a little bit depending on which generation and also whether it's an AMD or Intel CPU, but they all have something similar. And the goal is to not be able to not use predictions that were learned in a lower prediction mode or lower privilege mode in a higher privilege mode. We can also sanitize branch predictions. Essentially, one way is that we untrain, if we know which branch is likely to, or that the attacker might be interested in compromising, we can make sure that we can execute some code at some address that aliases with this when we enter the victim domain. So the first thing you do, for example, in the syscall entry, execute some code that maps the aliases with the location of this potentially vulnerable branch, so that it gets a new prediction that is harmless, let's say. And then if nothing else works, we have something called a branch prediction barrier or indirect branch prediction barrier that invalidates, well, originally all indirect branch predictions, but it invalidates a whole lot more as well. But this is like the big hammer. This is the last resort. You don't necessarily want to. You don't really want to use this unless it's really necessary because of the cost. And with this Inception attack that we made, it bypassed all of these types of restrictions and sanitizations. And we'll explain now how that's possible. So the first thing that we have the attacker training the branch in the victim domain. Instead of doing that, we make the victim domain train itself instead. So which is turning it into like some confused deputy scenario. And we can do this training after untraining or branch prediction barriers and stuff like this. And now the question is how we're going to train this instruction that is now somehow turned into a return. And we, like we already hinted at, we're going to train it without even using branches. So how are we going to do this? We're going to think about, we want to hijack returns because we like returns. So here's an example, like a concept, like we have some code. Imagine that the attacker can force the direction of this conditional to go in the direction that they want. So this means that we can have a mis-speculation here, so that we speculatively make a function call. And when we make a call, we also consequently get a return target prediction to the next instruction following the call. So that would be a return target prediction pointing to this leak gadget thingy. So the idea is that if we can make the victim domain speculatively execute a call, maybe later when we hit a return, we can actually take that prediction and execute the leak gadget to leak information. Of course, this looks very much like your average Spectre variant 1 case, so this is not really what we expect to find in the kernel. And this is also the theme of Inception that we're doing. We are combining phantom speculation with training the branch predictor inside the transient execution window. So we have something that we refer to as TTE, or training in transient execution. So this gadget we don't expect to find in the victim domain. It would be too much like a Spectre variant 1 and should be found and fixed. But there's something else maybe we can do. So when we have a mispredicted branch, it needs to be first predicted, and then it needs to be fetched and decoded and finally executed. And there are like mispredictions that are considered harmful and harmless. And the cases that are harmful are the ones that the mitigations are focusing on. So this means that these cases where we have like return, indirect jump, indirect call, these ones are the ones that we know that we get like a long speculation window because they can depend on memory operations, and we get a misprediction that lasts long enough to execute multiple memory operations and such. But there are other cases that are not mitigated, and because they are not really considered to be a security problem. So, but maybe they can help us to build something on top of. And one of these cases then is phantom speculation, where we have mispredictions that only reaches the decode stage and don't necessarily execute. And this means then that we can have for example, just NOPs, and we can inject a branch target prediction inside of there. And this means that we can take this concept code and turn it into something that is a little bit more realistic. We don't need to have any particular instruction here at all. We know that we can just inject a phantom jump anywhere we want that leads to somewhere where there is a call, there is preceding a leak gadget, and later then when we return, we hope to get this long misprediction window that we get from returns. Of course, nothing is easy, and so this is a little bit of over approximation of how it's going to work. But yeah, we're going to get into the details, so don't worry about that. Okay, so I'm just going to summarize this part. We're going to train the victim domain by executing by doing the training within itself instead of doing it from the attacker domain, and then the way we will make the victim train itself is using these short, harmless mispredictions. And yeah, with that we built a information leak that leaks arbitrary memory from the kernel, and we're going to now talk about how we did that. All right. So we have a branch predictor
containing this RSB, this predictor for returns. And so this just operates as a stack. So whenever we have a call, we push onto it, and whenever we have a return, we pop a target from it. And so we have a top of the stack pointer that keeps track of the last pushed entry. Yeah, just a recap. So we're going to be experimenting with the idea that Johannes just explained. We're going to be executing this call here to bar at function f in a phantom jump. And so we allocate these two functions, victim and f, and we prime the branch predictor such that there exists a jump prediction to f from victim. So when we execute victim, we have a phantom jump to bar, to this call, that calls to bar. And our results showed that this does push the address of leak gadget onto the RSB. But we also find that as soon as the phantom jump window is over, as soon as it's detected, it will just restore this top of the stack pointer to the original position. And so the return instruction right after will actually not end up executing the leak gadget. It will pop the right entry from the RSB. So the question is, what should we do? So we can manipulate the state of the RSB using this call in the phantom jump, but we do not end up executing the address we want. And so one might think, well, we can just execute a lot of returns, and eventually we'll hit the RSB entry that we're interested in. So the idea is quite similar, right? We just first have a phantom jump to a call, and then we push this address of the leak gadget onto the RSB, and then we just execute a bunch of returns and exhausting all of the other RSB entries, and eventually one return will consume the RSB entry we transiently inserted. And so we also experimented with this, but we found that this actually does not work. And so we were thinking about why this doesn't work, and we read some of the AMD manuals, and we find that they actually consider the case of incorrectly pushed entries under speculation, and so they have some recovery mechanisms against this. And this is also probably why this top of the stack pointer is restored. So they actually consider these cases. But we did not give up. Instead, we found a way to bypass these recovery mechanisms. And we found that we can do this by corrupting multiple RSB entries in a single transient window. So on Zen 1 and Zen 2, we found that we need to corrupt the entire RSB to bypass these mechanisms. Whereas on Zen 3 and Zen 4, it is sufficient to corrupt a large portion of the RSB. So how are we going to do this? How are we going to corrupt the entire RSB in a phantom jump? So one idea that we had is to make the call that we execute in the phantom jump recursive. So we're replacing f, this function f, with a function bar that calls to itself. And then immediately following the call, we have our leak gadget. And then again, we have a jump prediction from victim that to bar, so that we, upon execution of victim, have a phantom jump to bar, and we have a recursive call inside the phantom jump. And we found that this allows us to basically overwrite the RSB entries. And so now you can see it doesn't really matter anymore where the top of the stack pointer is pointing at, and there's not much to recover because we corrupted everything. And so the next return will have to execute the leak gadget. And that gives us a long speculation window we're searching for, allowing us to leak data. But now we're having another issue, and that is that this approach requires us to have a recursive call in the victim code, in our case, the kernel. And not only that, the recursive call must immediately be followed by this leak gadget. And so this is quite impossible to find. So in order to solve this, let's think about when the CPU actually wants to push to the RSB in order to ensure correct speculative execution. So we have the pipeline here at the bottom, and we consider that we execute this function f, which does a call, and the destination of the call is bar, and it immediately returns. Furthermore, we have a branch predictor state that knows all of this. It knows that there is a call to bar at f. It knows that there's going to be a return at bar, and the RSB state is set to an arbitrary state, depending on what previous calls we had. So if we now start executing f It will put f in the fetch target queue, and then the branch predictor will know that there's going to be a call to bar, most probably. And so it can already start fetching bar. And then it will again consult its internal state, and it sees, well, there's most likely going to be a return here. And so it will already, it wants to keep the pipeline full, so it will already start fetching whatever is on the RSB, which is B in this case. But B is, of course, not the correct location. We want to actually go back to F plus 4. And so the problem here is that we did not push F plus 4 yet onto the RSB because our call was not decoded. It's still in the fetch target queue. So what can we do to ensure this return prediction? How can we ensure that this return prediction will be correct? And so the solution is to push F plus 4 to the RSB before the call is decoded. So basically, whenever we have a prediction of a call, we already push to the RSB. So we experimented with this, and we found that AMD CPUs actually have this approach. So whenever there is a prediction of a call, it will already push to the RSB. And that means that if the prediction is wrong, and there's actually not a call, then we can have an arbitrary instruction pushed to the RSB. So here we have an example. We have bar again with an arbitrary instruction, which is not a call, but there exists a prediction of a call here. And when we execute bar, it will push the next address onto the RSB, which is the address of the leak gadget. And whenever the decoder realizes that it's actually not a call, it will just adjust this top of the stack pointer again. And so if we go back to our attack, we were looking for this recursive call, which was very hard to find. So what we can do instead is we can replace this recursive call with the recursive phantom call instead. So this bar call can be some arbitrary instruction if there exists a recursive call prediction there. So let's take a look at the final attack. In the kernel, we have this function that we just showed. We have an arbitrary instruction in the leak gadget. And then to make this act like a recursive call, we're going to allocate an address in user space that aliases with bar. And we're going to execute a call to bar at this location. So that this will give a segmentation fault, but it will insert a prediction to call to bar. And then we want to execute bar in a phantom jump, and we want to trigger that from this victim function. And so we'll again allocate an address in user space that aliases with victim, and from there we will jump to bar. Again, segmentation fault, but it will prime the branch predictor. And so when we now issue a system call, we'll at some point hit this victim function, and it will trigger a phantom jump to a location for which there exists a recursive call prediction. And so this will push onto the RSB, and we are in the state that we have the state that we wanted to have. The next return will now pop the address of the leak gadget and start leaking what we want. And note that we do not have any requirements on the victim code now. We do not have the recursive call anymore, or even a normal call. We just have a single return. So we measured how many of these entries of the RSB we can corrupt in a single phantom jump. And we found that we can corrupt up to 24 of these entries, which is quite a lot. And that means that on Zen 1 and 2, we can corrupt the entire RSB when it's operating in dual-threaded mode. And we evaluated Inception on Zen 2 and Zen 4. And these are the numbers that we obtained. And we also measure how long it takes to find the root password hash by locating etc shadow. So as a summary, we poisoned the return predictor by executing a recursive call in transient execution. And instead of finding this recursive call somewhere in the victim code, we just inject it with the phantom call primitive that we found. So the mitigation that we proposed is to execute IBPB. Johannes already talked about this. And the idea is that we just flush the branch predictor state so that our recursive call prediction will be gone. And so we measured how much overhead this will give us. And we have two observations here. The first one is that it is very expensive. So when it comes to performance, this is not a great mitigation. But if we look at it closer, we also see that there's something strange going on with Zen 3 and Zen 4, because they have a much less overhead compared to Zen 1 and Zen 2. And so we investigated a little bit what this could be, why this is the case. And we found out that on Zen 3 and 4, we do not flush any direct branch predictions from the BTB if we execute IBPB, as opposed to Zen 1 and 2. And so that means that we can make Inception work even after executing IBPB by just using direct predictions instead of indirect ones. And to solve this issue, AMD released microcode that basically adapts the IBPB behavior to also flush direct branches in addition to indirect ones. So another mitigation that we considered is automatic IBRS, which is a new feature in AMD Zen 4, preventing speculation on targets that were inserted in a lower level privilege. But if we look at what the promise is actually made by AMD, we see these two keywords, decoded, indirect branch, and so we can already think about whether this will work. So if it only works for instructions that are decoded as indirect branches, then this means that automatic IBRS must operate somewhat around here, after the instruction decode stage. And because our recursive phantom call operates at the very start of the pipeline, it doesn't really work. So automatic IBRS does not stop Inception either. Yeah.
Yeah, so they came up with a software approach, also for the parts that don't have automatic IBRS and such. So returns can be hijacked, so we gotta get rid of those. So actually, if you look at the kernel now, it has a single return instruction, and they do an interesting dance called SRSO. It starts with this SRSO alias untrained ret. This is for Zen 3 and Zen 4. First, we compile using this parameter for turning every function return into a thunk instead, an external thunk. So now every return is going to jump to a particular return that is like protected. And also, what we're going to do is, instead of returning, we jump to this thunk, then we make a call, then we adjust the stack pointer, so we will not take the prediction that was added by doing the call, and then we do a return. So in consequence, we get every single return misspeculating now as well, to stop this problem. In addition to that, actually, the x86 developers for AMD also does this alias untrain thing. And this we found pretty interesting. It's also an interesting dance with jumps and calls all over the place. So every time we enter the syscall, every time we do like a previous level transition, we make a call to this SRSO alias untrained ret, and then from there we make a jump to SRSO alias return thunk, and then from there we do a call to SRSO alias safe ret, and then from there we do the stack adjustment and ret. So yeah, this is a mess, but the purpose of doing this is to have the SRSO alias untrained ret at the line B here, and the SRSO alias safe ret at D alias in the branch predictor. So the idea is that they want to make sure that this return has not been tampered with by removing any predictions associated with it and replacing it. Well, it will be replaced essentially with a jump prediction, as it sees here. It looks like here. So we have, here's the first one where we do the jump, and here's the second one where we do the call, and then eventually we have the stack adjustment and the return. Now, these guys have been carefully placed in executable memory so that they alias in the branch predictor. And the reason why they do this is because they assume that the first return that is encountered can be hijacked, which is contrary to what we found. Because we only could hijack 24 entries out of the 31 entries, we actually had to execute a number of returns before we hit the return that we actually corrupted. And in this here, it seems that they actually think that it's possible to hijack the first return. So this is interesting, and we leave it as an exercise to the audience to see what you can do with that information. And yeah, so these software mitigations are like a necessary evil, and they are really, as you saw, is like really involved and complicated, and consequentially SRSO mitigations have gone through many versions. So we had the original one in 2023, then there were like some bug fixing to that, and then came some other x86 maintainer and were like, I wasn't invited to the party, here's my cleanup. And then there was some more cleanup, and then there were like, things were broken because of the cleanup, so people had to unbreak the cleanup, and it's all a crazy mess. And then there were more fix-up, and now we are already in April 2024, and we're still doing improvements to this mitigation, which is, of course, a bit annoying. So it also means that there are a lot of downstream kernels now running broken mitigations. For example, my own machine I found out, which is a bit concerning maybe. So, but you can test if you're using the SafeRet, which is the default mitigation for SRSO. Basically, you can just run this line here, which will measure the number of executed returns in kernel mode, and compare it, and also measure the number of mispredicted returns in kernel mode. So if both of those are pretty much the same value, that means that every return that you executed were mispredicted, and that means the mitigation works as it should. Yeah, so Inception on Intel is also something that we were interested in, whether this is feasible at all. But yeah, we looked a little bit at it, and we were not able to do it, and we tried to find reasons why we were not able to make it working. And there are some patents describing like a speculative part of the return stack buffer that will actually not be committed to the return stack buffer unless it has verified that you actually have a call that is being decoded. And this could be why we were not able to use transient execution to corrupt the RSB entries in this way. We did not invest much time on ARM, but they did release a advisory about Inception. Now I don't remember exactly what they said about it, but I think they said that it's up to their licensees to figure out what to do. No, I don't know actually what they said. I think they're not. It's worth checking out actually ARM. We didn't have much time to look at ARM, but I think in this case they were not super concerned with the problem. But they might be susceptible to training interaction and execution of the return stack buffer at least. Yeah, so it can also maybe poison the branch history buffer to enable branch history injection. But yeah, they think the risk is low of exploitation. So yeah, so this is what we talked about in the last year, training interaction execution we introduced. It bypasses prediction, sanitization, and restrictions. We introduced phantom call in order to corrupt return target predictions. And then, yeah, solving this problem is a bit complicated. Because IBPB is too expensive to use in fast paths. Yeah, even though something looks harmless, it can be used to create something that is a little bit less such. So yeah, which is the case for phantom speculation. So should we look at the demo again and see what happened here? One of these maybe has the root password hash. Can I send any commands to this? I just got the wrong one again. Maybe this way? Here's something. That looks like it could resemble a password hash. You can look at the other ones too. Yeah, okay. It's a side channel. They do like this. They never give you exactly what you want, only almost. This one looks pretty good. Okay, well, you can always repeat. Once you know where the secret is, you can repeat as many times until you verify that you actually have the secret. Yeah, I think we are out of time. So thank you for listening to our talk. If you have questions, if we have time for them, we're happy to answer them here in front of everyone, or we can do it also offline if you want to ask something that you want to share with everyone. Thanks.